Okay. Okay. Thank you, Thomas, for the introduction. Good morning, everyone. So before I talk to you about Try-Mopsa, I'm going to explain to you what Mopsa is. So Mopsa is a modular open platform for static analysis that was started around 10 years ago by an ERC grant awarded to Antoine Minet. And I'm going to explain a few of the key design decisions about Mopsa. So one is we really try to allow users to customize their analysis through the composition of abstract domains that they use. A second is that we try to ease for developers how they can write highly expressive relational static analysis that are able to infer, for example, linear constraints between program variables or ghost variables. And we also think that it can be used as an experimentation platform. We support analysis of, let's say, large subsets of C and Python. And there are also ongoing works on other front ends. So, for example, you can attend Mila's talk this afternoon to learn more about compositional OCaml analysis that she's working on. And I think it's somewhat good in the sense that it's academically competitive compared to other state-of-the-art tools that have been developed by really large groups for plenty of years in this software verification competition. So this is great, but then when we, for example, try to install Mopsa, so there is some package manager to do that, of course, but you can see we have plenty of OCaml dependencies in these white boxes and system dependencies in these gray boxes. And if you take the transitive closure, plenty of things could happen. So I think there are sometimes good reasons to try, you want to try out some software without the hassle of installing all those packages on your laptop. So Try-Mopsa is a way to do that. It's a scaled-down version of Mopsa that runs purely in web browsers. So you don't have to perform any installation here. And it will support the core features of Mopsa. I'll get back to that in a minute. And it features a responsive interface, meaning that you can even try to use it on your smartphone if you'd like. And I'd say it scales in the number of users because it's running purely on the client side, so you don't have to, the server doesn't do any computations there, so it's way more scalable than other approaches. And I'm also here to, I hope, entice you to use it for onboarding or teaching about static analysis. So in the remainder of the talk, I'll go a bit into the technicalities of how we achieved this creation of Try-Mopsa. Then we'll go for a demo, if all goes well, and then I'll discuss a bit the implementation. So just before we go into the how we compiled basically Mopsa to JavaScript, let's see a bit how Mopsa works. So Mopsa is a static program analyzer, so it needs a program to work on. We analyze different languages, so I already mentioned Python and C. We also have a language called Universal, which is, let's say, a toy imperative language working on mathematical integers. There are two other things the user can provide to Mopsa to customize its behavior. So one is a configuration, which is the composition of abstract domains you want to use for your analysis. And the second is command line options to, for example, tweak the fixed point engine and that kind of stuff. So now that we have all these inputs, the top level analysis will be able to do its work. So in there are iterators, partitioning, interval abstraction, congruencies, string abstractions, relational domains, and all this so does its computation, and there are different ways that Mopsa interacts with the user. So we have three different modes. One is called the automatic mode, so this is the most classical one. You just trigger the analysis, wait for the computation to finish, and then check the results, which is like a list of potential alarms. There is something we call the interactive engine, which is basically a GDB interface but working on the abstract state. So you can basically step through the abstract computations to look at the abstract state at each program point and see a bit more how the analysis is working. And then we have this DAP mode, which is basically the interactive engine, but working through the debug adapter protocol supported by some IDEs. So now to make all of Mopsa work in a browser, basically we try to compile everything to JavaScript. So Mopsa is mainly written in OCaml, and there is a compiler called JS of OCaml that will do most of the work. So with this, we get basically quite a few components already. And then there are the issues coming up. So for the parsing, our front end uses mainly this Mania library for parsing. So this works for Python and Universal. For the C parsing, we connect to libclang. And it's way too much manual work to make this work in Try-Mopsa for now. So for now, Try-Mopsa only supports Universal and Python as front end. The issue being that there are some ways to compile Clang to WebAssembly and that kind of stuff, but interfacing this with the JS of OCaml code is something you'll have to discuss with the OCaml Pro people. Another thing is we use arbitrary precision integer arithmetic. So this is the zarif library, which is also written in C. But hopefully there are some an equivalent stubbed version in JavaScript that is already available. So we just do a drop-in replacement here. So we get back intervals and congruences. Yay. And then there are relational domains. Apron, for example, provides polyhedra and octagons to Mopsa, and this is all written in C, so there's not much hope being able to run them as is. But hopefully there's been some work on verified polyhedra, and what's nice about them, for me at least, is that there are versions that are written in pure OCaml, so I can just compile them to JavaScript. I don't think it was the original intent of the people in Grenoble, but it's very nice for me. I can now have polyhedra in the browser. I'm really happy about that. And then floating point. So we have this interval abstraction for floating point that relies on setting rounding modes to be sound. And this is not supported. This setting of rounding modes is not supported by neither JavaScript nor WebAssembly. So for now, we don't have any floating point intervals working in Try-Mopsa. So this was a bit what Try-Mopsa supports. And then I'm going to explain a bit how it interacts with the web page. So we have two components. One is the top level that will handle user interactions, the rendering of the web page, and everything. We use something called the ACE editor so that people can edit their program in the web page with some tweaks to do some custom highlighting. And so Mopsa uses lots of anti-escape codes to render some text output. So we have some customized things here to render that into the web page. We also handle dynamic option generation because in Mopsa, if you, for example, enable a new abstract domains, it can trigger, it can create new options that you can customize. So we have to regenerate them every time the configuration is customized. And then basically this, so once the user is done setting their options and program, will trigger the computation in another thread called a web worker. So this is independent, so it won't freeze the rendering of the web page, for example. And this web worker will actually do the computation. And it will intercept basically what Mopsa is reading from the standard input or outputting to the standard output and forward them to the top level, so the top level can render them or ask the user for input. And we also rely on something called virtual file systems to embed our stubs, for example, for the Python libraries and the different configurations we provide as examples. So one thing I've mentioned before is we have this interactive engine. that works well in command line output, but this is like we're in that setting where we're having some kind of synchronous blocking interaction loop as a REPL. And this is quite difficult to implement in a web browser that usually require asynchronous interfaces. So here we rely on a library called sync-message that hacks some low-level browser APIs I won't talk to you about and enables synchronous communications. So now I'll get to a demo in a second, but before that I'll explain to you the program we'll consider for the analysis. So this is our universal language, so this toy imperative language. We start by creating a string A, and then an integer I is initialized to 1, and then we do this while loop until basically the character A plus the integer I is less than the character Z. We randomly stop the loop whenever we'd like, or whenever the randomness would like. And then we concatenate our string S with a new character. So for example, if I equals 2, this will be just the string B. And we increment I. So basically what this does is it computes a string S, which is either A or AB or ABC or the whole concatenated lowercase alphabet. And one assertion we may want to prove is that for any, basically any index, the character at any index minus the character A is strictly less than the size. So sanity check, for example, if you take C minus A in characters in ASCII codes will be 2, and this will be strictly less than 3. So this seems good. So let's go into this demo. You can also play with Try-Mopsa, it's available there. And let's try that. So if you go to the web page, you'll basically land on this page. So you can see that we have this code editor here. The analysis results will be displayed there. Then we have these configurations you can edit for the different abstract domains you use. And the options, we'll get back to those in a minute. So here I'm going to trigger a first analysis with, so you see we have different abstract domains. I'm not going to comment every one of them, but we have a loop iterator, for example. We do some function inlining, and we have an abstraction of strings that will just track their length. And the numerical part is just integers. And this is just the program that I've shown you. So let's trigger the analysis. OK, it works. Good. So here, the analysis succeeds, and we have two alarms. One is we are unable to prove that this is a valid subscript access, and the other is we're currently unable to prove this assertion. So let's try to investigate a bit why this is. And to do that, let's try this interactive engine I've talked to you about. So now you have like this GDB-like thing working. So you can put breakpoints. So for example, we'll try to understand what's going on here in our fixed point iteration. So we put a breakpoint and we go there. And then we can, for example, print the abstract values related to our string and our integer. So for the first step, we have a loop unrolling, so nothing interesting there. Let's continue. Second step will be the first iteration of the fixed point. Not that interesting either. So let's go to the next one. And here, basically, so one widening has been done. So you see that I has been generalized to the interval 225, but the length of the string is apparently just greater than 2, but not bounded anymore. So this is the source of the imprecision of one of the two alarms we had, because we don't really know here the length of the string. And here it's mainly because our interval analysis is unable to relate those two variables. So to change that, we can enable we can add our relational domain. So this will be polyhedra based on this verified polyhedra library. And we can run the analysis again. So let's go here and print S and I. And now you see, OK, let's do one more iteration, sorry. And now you see that we've been able to infer that I is equal to the length of the string S. So we're happy. It's a bit better, but if we continue the analysis, so we only have one alarm now. So we've improved our results, but we haven't been able to prove the safety of assertion here. And to do that, basically, currently on analysis reasons only on the length of the string, but you see this assertion here needs us to also reason on the contents of the string. So here we're going to do some kind of, let's say, container abstraction, and we want, so since our string can be of arbitrary size, we don't want to abstract every different character of the string in a different, for example, variable. So what we'll do is something called a smashing abstraction. It usually works on, for example, arrays of integers. So you have this array, and you'll say, OK, these elements of this array are just contained into this interval 1, 9. And here we just add this layer of, so we're using string, but we'll just encode them as ASCII characters. So if you take the VMCAI string, for example, it will be represented in this contents variable, numerical 1, between 97, so this is the ASCII encoding for letter A, to 118, which is the ASCII encoding for letter V. So we can now trigger this into, so we can trigger this string summarization abstract domain combined with our string length domain. I'm going also to disable the interactive engine and just print the abstract state here. And now you can see that, so we've been able, so this equality was already here before, but now we also have an inequality between so the contents of the ASCII codes of the string and 96 plus I. So, and this is basically equivalent if you, well, if you take these two, this is equivalent to this assertion. So the program is proved correct. And I'm hoping that I've shown you a few interesting things about the relational analysis that Mopsa can perform. So now let me discuss a few points about the implementation. So Mopsa is around 87,000 lines of code. Try-Mopsa is way smaller compared to that. So there's a few thousand lines of code for the web page. There is this top level and worker separation of work that is around 600,000, hundreds lines of OCaml code. We have this new VPL binding for our relational domain. And all this compiled and optimized by GS of OCaml is 3.1 megabytes, so that's not too heavy to load in a web page, I think, by today's standard, at least. And one interesting thing I find about this is we have no breaking changes with Mopsa, so I think it's really, we can have this. I'm hoping that we can maintain this for quite some time. Regarding performance, so I've tried to compare the binary execution of Mopsa on my laptop to the Firefox execution through some customized testing framework I'll present just after. And so these are really toy examples, and they are here just for demonstration purposes. But what we can see is, so we have 5 times slowdown compared to the native binary, but I think that in this context, the raw performance is not a priority. You really want just to show some examples or play for some examples for students, so that could be fine, and it's still reasonable. And then I try to assess the browser compatibility, because depending on your browser size or browser engine, it can be quite a mess. So here I use something called the Playwright framework, which is open source. And we wrote a few conformance tests, so to ensure that the different features of the analyzer work as expected. And they run on 3 desktop browsers, so I think Chrome, Firefox, and Safari, and 2 mobile browsers, so I'd say Chrome and Firefox, in 2 viewports, so either landscape or portrait. And so this enabled us to identify and fix several rendering issues, especially on mobile. And we also have additional tests to ensure that the toy programs we provide in the interface run in most of the configurations we provide. And just to give you an idea of how Playwright works in UI mode, so you can see here, this is basically the rendering of the test instructions that are written in TypeScript, and here there is like a nice rendering of step-by-step of the test. So I find it's quite fancy interface, at least for a static analysis person like me. So before concluding, I'll just want to mention a few different things about related work. So one is there's been ways to try analysis before, and they were mainly working on the server side. So there is interproc, banal, and Katerina's function. So they need less adaptation because you basically run your binary the binary of your analysis on the server side. But this creates, I think, maintenance and security issues. And case in point, I think only one of those 3 currently works right now. On client side, there's been some, quite a few developments thanks to GS of OCaml, or at least for the 2. So Chow Prolog is not in GS of OCaml, but so the Salto analyzer for OCaml by Benoit mostly. It has, you can try it through a web interface, and there is also a Binsec tutorial that was given at PLDI, but also yesterday, I think, that has some JavaScript versions where you can try things directly embedded in the tutorial page. And I think Try-Mopsa is the only one currently supporting relational domains and this interactive user input for the interactive engine, for example. So in Venice, there is this library for static analysis that Luca Negrini and others use also to teach. So there, students have to implement some new analysis. So Try-Mopsa is a different use case. I think we just want students to be able to play with analysis, understand how they work, but they won't be able to edit the actual implementation in the Try-Mopsa webpage. And there's been works on interaction with IDEs and also different combinations between concrete and abstract debuggers by other groups. And with that, so I've presented to you Try-Mopsa. This is a pure JavaScript version of Mopsa, supporting the core features of Mopsa, mainly relational domains and this abstract debugger. It works on smartphones and desktops alike. And I think it's really useful for demo or lightweight teaching purposes when you want students to play with different analysis of some toy imperative or Python programs. And feel free to use it here. With that, thank you for listening. I'll be glad to take any questions that you may have.
Are there any questions for Raphaël?
So thank you for the talk. So I really like this this way of having something that allows the students to really have like this very nice experience. And have you tried to work with some students, or do you have some user experience reports? What was easy to do? What was not easy to do?
So I don't have a cohort of students to try it on right now, but I know Francesco Ranzato used it a bit in his course this year. He previously used interproc, and I think he's mostly satisfied with it. I still have to see with him. One thing we don't do that interproc did was output program invariants per program point. State invariants per program point. We don't have a good way to show this in the interface right now. We can like show it here at specific points with these prints, but otherwise it's a bit difficult to do, especially with this fully context-sensitive approaches of functions we do. So I'm not sure how to handle this specific feature, but apart from that, it seemed to be working fine, and I don't have a larger cohort to try it on. But I'd be happy if you try it, let me know.
Thanks for the talk. You think it would be feasible to reuse your web interface so that other tools could also have a very nice interface like that? And how easy would that be?
With a bit of cleaning, I think it could be done, yes. For now, I haven't tried to generalize the interface enough, but so it's ugly in a way, but practical in another, that basically the web worker intercepts these standard input and outputs and then sends them to the top level. And I think this is general enough that other analyzer can just step right there. So we can try.
Okay, there's another question there.
Thank you for the talk. You mentioned that you don't have C because leapclang doesn't work on. I think that CompCert has a C parser, like a minier parser for C in the GPL version. Yeah.
So yeah, they do. So I haven't tried to connect it, and the main issue was my understanding of this front end is they probably need the pre-processed source code, so they don't handle. I'm not sure about what I'm saying here, so if someone more familiar with CompCert knows, feel free to interrupt. But I think they don't handle includes and all that, so if we use some standard library things, it's going to be complicated, and I don't want to go there. Because I think if you don't have the standard inputs and that kind of stuff, it's beside the point of C analysis.
Okay, any more questions? If not, let's thank Raphaël once more.
Thank you.